Dear audience, welcome to my presentation. I'm very honored that I have a very big audience, and after some presentation about the products and solutions that can build our future H2 environment, I will now give a more technical presentation that shall give you an idea how AVL can provide methodology and tools in order to improve the products and make it scalable for large use scale in the future. And the title is Innovative Methodologies for Fuel Cell Calibration. But before I go into detail, I may introduce the company AVL. The vision is to help the customers to develop clean and affordable energy for mobility. And to achieve this, there are three main disciplines in our company. First of all, the engineering services that will help and perform any kind of hardware design for many kinds of propulsion systems and also H2-based propulsion systems. Then on the right-hand side, we see the advanced simulation technologies, which are important part of the development in the virtual world. In the simulation world, we provide tools, 3D, 1D, CFD simulations, coupling of simulations, co-simulation, and so on. And in the middle part, the instrumentation and test systems, providing all the testing hardware, measurement devices, and also the software and methodology to achieve the testing in a very efficient way. So the title is, as I mentioned before, Innovative Methodologies for Fuel Cell System Calibrations. And now, before we start the technical part of it, I want to literally explain every term of it because it might not be clear to anyone and everyone. And in this context, innovative is meant as something that is connected with a fancy new idea. But fancy new ideas, you find a lot. They must also be useful, and useful and fancy is even not enough if you want to have innovation. That's maybe an invention, but it must also be easy to apply and scalable. So Mr. Berg might agree on this. So we need to find scalable solutions, not just possible solutions. The next term is fuel cell calibration. What do you mean with this? In any kind of powertrain system, also a fuel cell system, there is control units having a very complex control structure, and this is governed by a big number of setting, calibrations, maps, characteristics, and so on. And the task to find these calibration settings, which are numerous, is called then calibration, and to find best performance, but also meeting constraints that are governed by the use case. Maybe it's very warm, maybe it's in a cold environment, big scale, large scale, and so on. And the boundary conditions that will ensure the product durability and safety. But this is not the only boundary. There is a very important one, namely the limited time and effort to fulfill the work. Because as soon as the products are going from research to bigger scale and serious production, this is a very important factor. And if we see now the middle part, methodologies, how can we reach this? With innovative methodologies. So these methodologies we will explain a bit in the next slide. What is meant by a methodology? It's the approach how to calibrate. And to name some of them, it's a very obvious one. You go to a test bed, there is a fuel cell system installed, everything is working, and the engineer just tries to adjust some settings on the control unit and sees the result. It's getting better, it's getting worse, tries another parameter and plays around a bit, trial and error. And that's not the only one. There is, of course, more elaborated methodologies something like a one-factor at a time approach, where you have one calibration factor, stoichiometry of the cathode, for example, and you change it in some steps and draw in Excel or wherever on a piece of paper the curve of the efficiency, and you will find there is an optimum efficiency, and this you will take. But then there is other parameters and other parameters that will interact. But still a good methodology for the start. Another thing could be a step response. Do change an actuator in a step, look what the system does, and do some analysis, and do a PI controller tuning. Then there are more elaborated things like design of experiments, where you just expand this one factor at a time approach to more dimensions. You change the stoichiometry, the pressure, the temperature, the current demands, and so on, all at once. And as a result, have a minimized testing effort when you build afterwards empirical models, and you need less time on testbed. So this is the idea. But there could also be an automated online optimizer, some system that's automatically, without the interaction of an engineer, changing the settings and finding best solutions, or everything combined, automatic execution, DOE with active DOE, we will hear later, model-based calibration, online optimization. So if we see this collection of methodologies, we can draw two axes. And on the first axis, we can see it's from simple to advanced. It's clear the manual trial and error is not so advanced, but there is a very important second axis, and that's the ease of use, and connected with this, the frequency of use. In commercial calibration projects, we see very often that the personnel there will approach the easiest way if you have some small problem. So manual trial and error is fine. But for more complex problems, you need more complex methodologies. And these methodologies are there. They are inventions, but we also need industrialization, because otherwise it's not scalable, and otherwise there is no innovation. So this is meant with terminology innovation. And to find out now about how we can achieve both invention and industrialization, we see next slides the comparison between the simpler ones and the high elaborated ones. Starting with just a sketch how the calibration routine works on the testbed. So there is the testbed, as I said, you change the calibration, get performance response. And this response is recognized by either a human, a testbed engineer, manually changing something, and then the thing goes in circle, or an automation system, an automated optimizer does the same thing. So it's going in an iterative way and tries to find the best settings based on the targets and constraints. And the result is a calibration. And the calibration is a set of numbers that define the characteristics what the control unit shall do. That's fine. So in some real case, what will happen there maybe? What happens in reality? The calibration project outline is the system is installed on the testbed, but in week 41 there is another thing, so it must be removed 40. Okay, and there is budget for 4 weeks. And in week 40, just in time, the calibration is done, the target is met, everyone is happy. Until there is new targets, new constraints. Could be that the customer decides, I want to go to a market where it's hotter, colder. There is different requirements on the dynamic behavior or something like this. What do you do? It's not on the testbed anymore. Calibration must be done on the testbed, but it's not available. And here now comes into game the active DOE model-based calibration. How we can do this here? We have the same situation, calibration change and response, but in this case, there is a system installed with an online model. So while the test is running, the results, the responses are put into an artificial intelligence model building, and this will build an empirical model while the test is running and feeding an online optimizer, as well as designing of experiment in a smart way. So you only test what is needed, because beforehand you don't know if this combination works or not, but this should know. And same story, iterative process, but now we have a calibration plus a system model. And this we could use later, because same situation appears, only available until week 40, but this time we are faster, because the methodology is done in a way that you have automated running and running less points for same information. And when in week 42 the customer decides to do something else, that's no problem, because we can do the calibration in office using the empirical model. So by this, I hope it was explained where the invention part is coming from when we look at this slide. The second thing is, this looked rather complicated. Is it really applicable for a broad range of users? So industrialization is very important. How can we attack this? The key is an integrated workflow. So the workflow begins with designing and setting up a test, where the engineer decides, for this task, I must try to change the stoichiometry, change the pressures, change some temperatures, and so on, and within a range. So these are some basic informations. And with these basic informations, an automatic test must be executed. And automatic test execution sounds easy, but if it's a system that was not automated before for complex tests, first of all, you need all the interfaces, and then the ability to run safely just some random points without human interaction. So the handling of limit violations is crucial, not to shut down everything, but to continue. And all the stabilization routines and so on should be available without scripting, so without 2 months of coding that should run. And as explained before, there is this methodology of active STS2E, so maximizing the information. I will not go to complete details. Please ask afterwards. And also one very important aspect is that the models, the empirical models that are built, are done in an automated way. So there is not the expectation that the user is a mathematician. It's supposed to be a one-button click, and for the power users, they can modify something. And this last and very important part, there must be an optimization, and the optimization results must be processed in a way that it's fitting in the control unit. It's not accepting just some raw numbers. You need to have nice maps. The maps need to be flat in order to be usable in a real application. And all this workflow is industrialized with ABL Cameo, which helps a lot. So how much does it help? Innovation is described how it's done. Let's have a look at example for PM system steady state optimization, efficiency optimization. What is the task here? So the current is something that is demanded from the user, from the construction machine, from the combined heated power, whatever. And the other things might be boundary conditions, such as the coolant temperature. A cold start is a cold start. You cannot choose temperature immediately. But the other things should come from the control system, and that must be calibrated. And all of these things must be varied and tested on testbed, but not in all combinations, just in smart way of combinations. To find maximized system efficiency, but also respecting humidity and delta voltage limits to maintain the safety and durability. And all of this, you can imagine, is not so easy in a manual way. But still, there was in the powertrain engineering a development of the fuel cell system you see here. It's also exhibited. And there was the comparison some years ago. The experts, the fuel cell calibration experts, they did a manual approach and tried their best to calibrate this task. And they took around 4 weeks. Then colleagues of mine with the methodology came in and tried to apply exactly what we have seen before, this integrated workflow with active TOE, model-based calibration, and the efficiency was improved. The effort was much less, 50 hours of testbed runtime, mainly nights and weekends, so it's not affecting the work time of the engineers. And this is now an industrialized methodology used in more than 10 calibration projects within AVL. So, to give an overview, this is a methodology giving new ideas in a scalable way. And there are many fuel cell calibration tasks like system efficiency optimization or transient optimization for fast response. But also in the simulation world, this can be applied. To make a conclusion and give you some takeaways. So there are methods to improve calibration process, but they must be innovative and easy to use. And with an integrated workflow available in AVL Cameo, this is the case. And if you decide to integrate something like this, the news is you cannot focus just on this one application. You can use it also in other things like simulation, mill environment, SIL environment, or hill environment, and also in completely different technologies, SOFC, SOEC, or stack testing, or also H2 combustion. With this, I want to thank you for your attention. If you have any questions, please go ahead and ask, or also visit our booth at L11, or visit our website, avl.com. Thank you for your attention.